So in the last session, we completed our shunt DC. We have already completed the shunt DC motor and the separately excited DC motor. We started this DC series motor, and we discussed the terminal characteristics of a DC series motor, the speed torque characteristics. Now we'll be talking about the speed control of DC series motor. So again, you actually have only two methods of controlling the speed in the case of a DC machine. It's either the armature control or the field control, or both. Fine. In this case, in case of a DC series motor, there is only the armature control. There is no field control. So by armature control, we simply mean changing the applied voltage. So if we increase the applied voltage to this motor, you can see from the equation the armature current will increase. An increase in armature current means increase in torque induced. Increase in torque induced means higher speed is achieved. With higher speed, EA will again then increase. That will cause IA to fall back and torque induced to become equal to torque load again. So the steady state will again be achieved, but at the cost of higher speed values. So this is your armature control strategy. You can increase the applied voltage to increase the speed. You can decrease the applied voltage to decrease the speed. And as we have discussed previously also, we tend to basically use the armature control strategy to control from 0 to base speed or the rated speed of the motor. Why we do not go for the field control strategy in case of a DC series motor? We do not use field control here. Why do not we use the field control strategy? Because RA and RF, they are in series in case of a DC series motor. So as I've listed what are the disadvantages of increasing RA for speed control, now the same disadvantage will apply to increasing the field resistance in case of a DC series motor. So if we increase the field resistance to change the flux, but what we are doing, we are also now changing the armature current. Because of that, we are also increasing the power losses in the system. So it's not a practical approach to increase the resistance, the field resistance of the winding in case of a DC series motor to achieve speed control. We can do it, but it is not a feasible method. Moreover, it will in this case, in case of a DC series motor, changing RF will actually not only change the flux value, it will also change the armature current directly, because in this case RF IA is actually dependent upon the field resistance. So on one end, if you are increasing RF, you are decreasing the flux so that the speed of the motor increases. But on the other hand, increasing flux will decrease the armature current. That will actually cause a decrease in speed. So they will actually be counterproductive to each other. Although there will be a difference between what the magnitude and whether the flux increases more or the armature current decreases more, but nonetheless the effect will be there. Moreover, because of the power losses associated by increasing a series resistance, we do not prefer to use field control strategy in a DC series motor. Now coming to our next topic, next type of motor, we have the compounded DC motor. Now, what is a compounded DC motor? It's basically a combination of both shunt and series DC motors. So what does this mean? We can have a motor like this. Terminal voltage, we are applying the terminal voltage. Line current will be flowing through here. Armature current will be flowing through here. EA is the voltage across this armature. RA is the armature resistance, that is the resistance of the armature winding. The resistance of the field winding is actually separated into two parts. One part is a field winding that's in series with the armature resistance, and another part is the field winding that's actually in parallel with the armature resistance. So we have two field windings here, one is in series and another one is in parallel. It can either be in this fashion or it can be like this. This is your terminal voltage, this is the line current, this is RA, this is RFS, this is RFP, this is LF. Fine, this is your inductance of the field winding, plus minus EA. So armature current is flowing through this path in this direction. IF is the current flowing through this path. So again, the field winding and the armature, the field winding is connected in series as well as in shunt with respect to the armature winding. Now it can be either in this fashion. This is known as the long shunt connection, and this is known as the short shunt connection. So you have the long shunt connection and the short shunt connection. So in the long shunt connection, the field winding is in shunt with the armature, but a little bit farther, you can say, actually. And in case of the short shunt connection, the field winding is directly in parallel with the armature winding, and another part of the winding that's in series is in series with the applied terminals of the DC motor. I would actually like to also incorporate inductance of this series field winding as well, here as well as here. So you have a series field winding having its own inductance LFS, this is LFP, this is LFP. So you, in case of a long shunt connection as in case of a short shunt connection, the difference is between whether the series field winding is directly in contact with the armature resistance or it is in series with the actually the parallel path, whether it is directly parallel to the armature as in case of a short shunt connection, or if the field winding is in parallel with the combination of the armature resistance and the series field windings. Fine. So based upon this, you can differentiate the compounded DC motor as a long shunt connection or a short shunt connection. A long shunt compounded DC motor and a short shunt compounded DC motor. This is one classification of compounded DC motor. Another classification of compounded DC motor can be cumulatively compounded. So these are the same motors, it's only depending upon the flow of current in these circuits, we can differentiate them as cumulatively compounded or differentially compounded DC motor. So what does this imply here now? Now I'll take only one of these two. You have, say for example, I'm taking the long shunt connection. This will be both true for the long shunt as well as the short shunt connection. This is RA and this is EA. Current I is flowing in this path. Current IF is flowing in this path. This is RFS, the series field winding. This is RFP, the parallel or the shunt field winding. This is LFP, this is LFS. Fine. So current is flowing in this path and the current is flowing in this path. Now depending upon the windings, we will be deciding the polarity of the inductive parts of these systems. Say for example, the currents in both directions are in such a fashion that it produces a positive polarity at this end and positive polarity at this end, shown by the dot connection. You might have studied the dot convention in your network analysis course. The dot connection is basically depending upon the direction of current and the flow of current through the windings, whether it's a clockwise rotation or anti-clockwise rotation, you can decide the polarity, and accordingly the dot convention here shows. Now in this case, if the dot convention is like this, dots are on these two sides of the windings, then the magnetomotive force will basically add up shown by dot. I'll write here MMF in the two coils of the field windings. These are both field windings. MMF of the two field windings will add up. So if the parallel field winding is producing an MMF equal to MMF shunt, and the series field winding is producing MMF equal to MMF series, so the net MMF that will be produced in this case will be MMF series plus MMF shunt. Now in another case, if the field windings are wound in such a fashion, if the current flow in the basically results in the magnetomotive force being subtracted, that means say for example in this case I'll now show this by a triangle here. Fine. So there is a triangle here and there is a triangle here. So that means what is happening? The windings are the nature of windings and the nature of current in the two field windings is such a results in the two mmfs, the polarities to be produced at opposite ends of the field windings. What will happen because of that? mmf of the two field windings mmf of two field windings will subtract. So mmf in this case, the net mmf will be equal to mmf series minus mmf shunt, or mmf shunt minus mmf series, depending upon the dot convention. Fine. So because of the nature of winding, whether it's a clockwise or an anti-clockwise winding, and the direction of current flowing through the windings, we can basically decide the polarity of the voltage on the we can decide the polarities on the field windings, on the series field winding as well as the shunt field windings, and depending upon that polarity we can decide whether the two mmfs produced by the individual field windings, the series and the shunt field windings, whether they will be adding up or whether they will be subtracting each other. If they are adding up, it will be referred to as a cumulatively compounded DC motor. This is and if the two mmfs subtract from each other, it will be referred to as a differentially compounded DC motor. Now this is true for both cases. It can be it is valid for this long shunt connection as well as for the series shunt connection. So we have actually done two classifications of compounded DC motor. A compounded DC motor has two sets of field windings. It has a series field winding as well as a shunt field winding. That means one winding is in series with the armature and one winding is in parallel with the armature. Now, depending upon first of all the connection, we can classify the compounded DC motors as a short compounded DC motor or a long shunt DC motor. Short shunt DC motor is where the shunt winding is in parallel with the armature winding directly. In the long shunt connection, the field winding is in parallel with the armature and the series field winding. This is one set of classification. Another set of classification of the compounded DC motors is depending upon the now since we have two field windings, we will be having two different magnetomotive forces, two different fluxes produced by these field windings. So depending upon the polarity, whether the two mmfs in the two field windings will add up or they will subtract, we can have a cumulatively compounded DC motor or a differentially compounded DC motor. So we can so we have discussed two different classifications of compounded DC motor. Now this cumulatively compounded DC motor as well and differentially compounded DC motor is valid to both long shunt connection as well as the short shunt connection. Now if we have the long shunt connection, we'll be having one set of KVL equations. In the short shunt connection, we'll be having another set of KVL equations, though in general we can write in both cases one thing is valid. IA is equal to IL minus IF, or you can say line current is equal to IA plus IF, or IA is equal to IL minus IF, where IF is Vt divided by Rf. Fine. So Vt is the voltage that is applied. If we are talking about the long shunt connection, and also in this case, in the long shunt connection, Ia is equal to, not Ia, Vt is equal to Ea plus Ia Ra plus Rfs. This is Rfp. So this is your long shunt connection. This is IL here. So IL is equal to Ia plus If, and If is equal to Vt divided by Rfp. If we are neglecting now the inductance, I'm talking about steady state connections, steady state values. In the steady state, inductance will be short in this circuit, and therefore Vt, if we apply the KVL in this loop, Vt is equal to Vt is the voltage across this point as well. So Vt is equal to Ea plus Ia Ra plus Rfs. Fine. So this is for your short shunt connection. And the magnetomotive force, what will be the magnetomotive force? F net will be equal to Ff plus minus Fs, Ffp plus minus Ffp minus FAR. So the net magnetomotive force, now depending upon whether it's a cumulative compounded DC motor, these equations are valid for the long shunt connection. Long shunt connection. The net magnetomotive force will be equal to FFP, where FFP represents the field, the magnetomotive force produced by the parallel path, plus minus FFS, where FFS represents the magnetomotive force produced by the series windings, plus minus here represents whether it's a cumulatively compounded or a differentially compounded DC motor, minus FAR. The armature reaction is always going to subtract from the two main fluxes. So we know that the armature winding will also produce its own magnetomotive force, and that is always in phase opposition to the main field produced by the field windings. So minus FAR, the armature reaction is always subtracting here. So this is for your long shunt connection. For the short shunt connection, look at the short shunt connection diagram. IL is again equal to IA plus IF. So you can say IA is equal to IL minus IF. Fine. And Vt minus IL RFS this is your short shunt connection. In this case, Vt minus this voltage, if we are talking about steady state conditions only now, minus IL RFS, this will be equal to the voltage at this point. Fine. So therefore that voltage will be equal to Ea plus Ia Ra in this case. So therefore you can also say Vt is equal to Ea plus IA RA plus IL RFS. Fine. So you need to find out the line. You need to know both line current as well as armature current in the short shunt connection to find out VT, while as in the long shunt connection you only need to know the value of IA to find out VT or find out EA. VT will be actually given in a DC motor. To find out EA, we will require both IA and IL in a short shunt connection. In case of a long shunt connection, we only need to know the value of VT and IA in case of the long shunt connection. So this is your equations, and also you can write IF is equal to VT minus IL RF S divided by RFP. So going back to the diagram, if you want to find out the field current, you need to find out you need to basically solve the KVL in loop 1. So these are your different equations, and as far as the magnetomotive force goes, F net is still equal to F, the field produced by the shunt winding, plus minus field produced by the series winding, and minus the field produced by the armature. That's actually referred to as the armature reaction. So this is your equivalent circuit, different types and equations of a compounded DC motor. Now going to the torque speed characteristics of a compounded DC motor. We'll be doing the torque speed characteristics of